If the slits and screen are very far apart, you can assume the two beams have taken parallel paths. Hello. Today I'm going to derive the equation for Young's double slit experiment, which is W is lambda d over S, W being the fringe spacing, lambda being the wavelength, d being the distance from the two slits to the screen, and S being the slit spacing, the distance between the slits. Now, to do this, I'm going to have to do something which physicists always do across many different branches of physics, which is make an approximation. Now, this may seem strange, as this may be the first time that you've seen something like this, but it's completely normal, because what it means is we'll get an equation which works to within a very small percentage of the correct value. So it means we'll get answers which won't be exactly perfect, but which will be very close to reality. And that's okay, because that's the nature of scientific experiment. All experiments come with some uncertainty. So it's fine for our equations to also come with that small amount of error. Now, the approximations that we use differ across different branches of physics. Today, we're going to use an approximation which assumes that if the distance of the screen from the two slits is very large compared to the fringe spacing W, we can approximate that the two beams of light from the two slits have travelled parallel to each other. Now, obviously, they haven't travelled parallel to each other because they do meet at the screen. There are two different beams of light coming from two different slits that meet at the screen, so they're definitely not parallel to each other. But if the distance, capital D, between those two slits and the screen is big enough compared to that tiny distance W from the centre of one bright fringe to the centre of the next bright fringe, we can make that assumption. And I'll show you how that works now. So you will remember this diagram from the previous lesson on Young's double slit experiment. You can see the two slits, S1 and S2, and a point on the screen P where the first bright fringe from the centre is seen. So constructive interference must be happening at this point. Since it's the first bright fringe, the path difference between the two beams S1 to P and S2 to P must be exactly one wavelength, which I show over here. S1P minus S2P has to equal m times lambda for constructive interference. So at this point, P, which is the first bright fringe, m must equal 1. Now, that path difference, lambda, is equal to the difference in path between S1P and S2P. And I'm going to add that to my diagram. So I'm going to add a point Q over here. Here is the point Q. I've chosen the point Q to make the distance QP and S2P be exactly the same, which means this distance here, S1Q, that is the path difference. So S1 to Q is the path difference. That's the difference in the paths between the two beams, S1P and S2P. And what I'm going to show is that this little triangle here, S1, S2, is similar to this big blue triangle here. So that's from M, which is the centre of the two slits, to O, which is the central bright fringe, to P, which is the first bright fringe. And the way I'm going to do that is as follows. This angle here is theta. That's the angle between the horizontal and a ray from the screen to the slits. Now, because I'm saying that the distance d from here to here, the distance capital D, is very big compared to the distance w, all three of these lines, S1 to P, M to P, and S2 to P, they are all parallel to each other. I know it doesn't look like that on the diagram, but if I was to make the distance d really big over here, the lines would look almost parallel to each other. Therefore, if this angle here is theta, that means that if I put a horizontal dotted line here, this angle must also be theta. Now, if this angle is theta, this is to within a tiny, tiny percent perpendicular to the rays. So this angle here is 90 minus theta. And because this is a vertical and this is a horizontal, that makes this angle theta. Now, I can hear you at home, I can hear you complaining that those are not exactly right because this is not exactly at right angles to that, and you're right. But if the distance capital D is very, very, very large compared to the distance W, you can consider all three of these lines to be parallel. You can also consider this from Q to S2 to be perpendicular to the beams of light. Therefore, I now have two triangles which are similar. I have the triangle which looks like this, S1, S2, Q, and I have the blue triangle which looks like this, O, P, M. In both of those triangles, this angle here is theta, which to a very good approximation, those two angles theta are the same. Also, the distance from S2 to Q and the distance S2 to S1 are approximately equal. And the distance M to O and M to P are approximately equal, which means I have similar triangles. Therefore, I can do the following. I can say that S1 to Q divided by S1, S2, which is the ratio of the opposite to the adjacent, which is tan theta, is equal to OP over OM, which again is the ratio of the opposite to the adjacent tan theta. So the ratio of S1Q over S1S2 is the same as the ratio of OP to OM. Now S1 to Q is the path difference. That's the path difference, which we've said is lambda. S1, S2 is the distance between the slits, which is S. OP is W, our fringe spacing, and OM is the distance from the slits to the screen, which is capital D. And you can see all I need to do is rearrange that and I get Young's double slit formula. That formula only works if the distance capital D, the distance from the slits to the screen, is very, very large compared to W, the fringe spacing. Finally, here is a little tune about the derivation that I just did. Now you'll notice I use the London pronunciation of the word path to make it rhyme with the word apart. As a Mancunian, I do say apart and path, but I will be changing my accent for the purpose of this song. So here we go. I still don't know how to play the ukulele very well, but I'll try my best. So, if the slits and screen are very far apart, you can assume the two beams have taken parallel paths. If you have any questions or comments, please comment below. Please like the video if you liked it. And also subscribe, because then you'll see any other videos that I post about A-level physics and about GCSE physics. Thank you.